Welcome back to the Deep Dive. Today we're wrestling with one of the most surprising, quietest forces in all of physics. Imagine two perfect, shiny metal plates, mirrors, if you like, just sitting perfectly still in an absolute vacuum.
Right.
They aren't charged, they aren't heated, they're just there, separated by a tiny gap, and yet they pull together. This tiny, weird, measurable attraction is the Casimir effect.
It's just physics gold. And the standard explanation, the one you read in the textbooks, it revolves around this idea that the vacuum is not empty. It's actually brimming with virtual particles and fluctuating fields.
The zero-point energy.
Exactly, the zero-point energy of the vacuum. And the force arises because there are fewer allowed field modes between the plates than outside them.
But that standard story, it comes with these huge infinity problems, and, well, we're not sticking to the standard story today. We are going deeper. Our mission is to try and understand this force entirely through the lens of motion theory. It's a fascinating framework that views this attraction not as a byproduct of some infinite energy, but as the universe adjusting its mode ledger.
Precisely. For motion theory, when you introduce those plates, you force the universe to recalculate its allowed rhythms. It's not about tapping into some infinite energy well. It's about how changing structure changes the allowed patterns of motion. So the Casimir force is just the energy cost, the fee, if you will, of that necessary recalculation.
I love that idea. The force is the cost of recalculating rhythms. Okay, let's map this directly onto the original calculation, the one that actually proved this force existed. Hendrik Casimir, 1948.
Right. So Casimir looked at two ideal boundaries, perfectly conducting parallel plates, separated by a distance we'll call it. And this is all theoretically at absolute zero temperature. Crucially, he wasn't interested in the total energy of the vacuum, which everyone kind of knew would be infinite. He was only asking about the net force generated by the electromagnetic modes that those boundaries allowed.
And the quantization is what makes this manageable, isn't it?
It is. It's the key. Between the plates, only standing waves can fit. This means the electromagnetic field is restricted to discrete, specific wavelengths. Outside, though, the field can have any wavelength it wants. So what Casimir realized is if you sum the zero-point energy, that's 1/2 a shoo for all the modes, and then calculate the difference.
The difference between the plates being close versus the plates being really far apart.
Exactly. When you do that, the infinities just cancel out.
Infinity minus infinity equals a tiny, measurable number. That is the ultimate physics trick.
It's the first great act of what we're calling mode bookkeeping. And the resulting pressure, it scales incredibly quickly. The force per unit area is proportional to 1 over to the 4th power.
So if you have the distance between the plates, the attractive force gets 16 times stronger.
16 times. It's a huge effect at the nanoscale.
Okay, here's my critical question then. Standard quantum electrodynamics, QED, it already handles this cancellation beautifully just using boundary conditions. Why do we need the whole motion theory framework, the coherence ledger and all that, just to rename what we already seem to know?
That is the perfect question. We need the MT lens because it changes what we think we're actually measuring. In standard physics, you measured an energy difference. In motion theory, you're measuring the retuning. We interpret that one over O to the 4th force as the literal energy required for the structured motion of the field to accommodate the new boundaries. It ties back to a core MT concept. Mass is the resistance to retuning. If the plates have an effect, a force, it's because the field's motion resisted having its configuration changed.
Okay, let's nail that down because this feels like the core distinction. So, the textbook view, total vacuum energy is infinite. Casimir's math just shows that only changes matter.
Right. Motion theory takes the guesswork out of the semantics here. We don't say the infinite baseline energy doesn't exist. We say that the zero-point energy is simply the baseline motion of every mode, established by universal quantization. And we treat that baseline as already paid by the universe.
So the plates aren't tapping an infinite cosmic fuel tank. They're acting more like a cosmic zoning ordinance.
Exactly. That's a great way to put it. They delete certain standing wave patterns that would normally exist, especially the long wavelength, highly coherent ones, and they slightly shift others. Casimir forces arise because you rearrange which modes exist and how they can synchronize. It's pure mode bookkeeping.
You're not tapping an infinite tank. You're just nudging how the existing traffic is organized.
That's it.
That distinction clarifies everything. It shifts the whole focus from this vast, untapped energy reservoir to just localized accounting. Let's move this to real-world applications because, ideal parallel plates don't exactly exist.
Well, first we have to touch on the link to single atoms, the Casimir-Polder link. Casimir and Polder extended this whole idea to neutral atoms. It turns out the familiar van der Waals force is actually a retarded Casimir force at long distances.
Retarded, meaning the speed of light is finite, so the interaction isn't instantaneous.
Precisely. And that time delay changes the scaling. Short-distance van der Waals falls off very quickly, around 1 over r to the 6th. But in the retarded regime where light speed matters, the scaling steepens to 1 over r to the 7th.
So it's like, at a long distance, the gossip between the atoms is throttled by the speed of light. The rumor mill slows down, and the attraction weakens faster.
That's a perfect analogy. And when we move from perfect conductors to real leaky materials, metals, dielectrics at room temperature, we transition to the really powerful Lifshitz theory.
Lifshitz generalized the theory to account for all the real-world complexity. Finite conductivity, temperature, loss.
He did. He achieved this by using frequency-dependent dielectric functions and summing over something called Matsubara frequencies.
Wait, okay, let's unpack that jargon moment for a second. Matsubara frequencies. That sounds incredibly abstract.
They're mathematical tools, yes, but the concept is actually pretty simple. They just allow us to account for thermal effects and material loss. They let us describe how sticky or leaky real materials are when they interact with EM fields instead of just treating them as ideal mirrors.
That makes sense. They're just accounting for the imperfections. So how does motion theory map those imperfections?
In MT, materials become definitive motion filters. Their dielectric response tells us precisely how they phase shift and dissipate the EM modes. And this is where the core MT coherence concepts come right into play. When materials heat up, that's thermal entropy, S-thermal, they decrease the quality factor of the modes, which means they decrease the system's ability to maintain organized, coherent motion, or S-coherent. The Casimir force is just the net result of all these filtered, thermally influenced modes trying to satisfy new boundaries.
This moves out of the lab and straight into engineering headaches, doesn't it?
Sure.
We're talking about micro-electromechanical systems, MEMS.
Absolutely. At the nanoscale, gravity is negligible, but Casimir forces are huge. They cause unwanted stiction components literally pull themselves together and lock up. I remember reading about early microaccelerometers where designers had to actively fight stiction by patterning surfaces with specific textures. At this scale, the structured motion of the EM field isn't some background noise. It is a fundamental design constraint.
The solution is fighting geometry with geometry. You intentionally pattern surfaces or use thin films to physically change the density of modes between components, trying to create patterns that minimize the attraction. You're actively engineering the mode ledger to prevent disaster.
Precisely. You're forcing the universe to recalculate in a way that is beneficial to your tiny machine.
Speaking of recalculation, let's talk about the most mind-bending application here.
Okay.
The dynamical Casimir effect. If you move a mirror fast enough, you can create real, observable photons from the vacuum.
It's astonishing. You can't actually achieve the required speed with a physical mirror, but experiments use superconducting circuits, SQUIDs, effectively, to modulate the effective boundary condition at gigahertz rates. And they observe correlated photon pairs just emerging. It looks like creation from nothingness.
So if the vacuum coughs up light, what exactly is motion theory suggesting is the source? Is it just turbulence in the field?
It's more targeted than just turbulence. You are rapidly retuning the allowed modes. You're changing the size of the box so quickly that the structured motion of the field can't maintain its ground state configuration. The mode patterns and their phases, they just lag behind the changing walls. That massive phase difference, that lag in reequilibration, it has to be paid back to the universe.
And the payment is in photons.
Yes. The difference between the original coherent state and the rapidly perturbed state, it manifests as emitted photons. It's the universe throwing light at you to balance its ledger because you yank the walls around too fast.
This circles us back perfectly to the big picture and why motion theory really matters philosophically, the cosmological problem. If vacuum energy is infinite, why doesn't it cause the universe to expand at a ridiculous rate?
Right, the notorious issue. If you naively couple the textbook's infinite vacuum energy density to gravity, you predict a cosmological constant that is roughly 120 orders of magnitude larger than what we actually observe.
Which is the worst prediction in the history of physics.
It is. MT avoids this catastrophic failure.
Because
MT asserts that you never couple the raw baseline zero-point energy to gravity. The universe already paid for that baseline. Observable Casimir forces. And thus, what couples to reality come only from coherence shifts in the field's modes, which are induced by boundaries. You only couple the coherence shifts that survive after the uniform background is subtracted. We're talking about localized bookkeeping, not the entire cosmic balance sheet.
This fundamentally changes what we're looking for then. We're looking for changes in coherence capacity, not infinite energy density. And this framework allows for truly testable, falsifiable predictions that can bridge the theory with actual experiments.
Absolutely. Let's look at three key tests based on this mode ledger idea. The first is prediction one, which focuses on phase-engineered Casimir tuning.
Okay, what's the experiment?
We propose building metamaterial mirrors that allow us to change only the phase response of the boundaries, so how the light waves reflect, while keeping the reflectivity magnitude itself constant. Standard theory is sensitive to this, but MT makes a much stronger claim related to heat.
And that stronger claim involves the coherence ledger, right? This is where we pay for order with heat.
Exactly. MT predicts that this subtle phase change must still alter the Casimir force, and the heat generated during that tuning, S thermal, should correlate exactly with the change in coherence capacity. If we can't measure that predictable heat signature correlated with the force change, the MT coherence ledger hypothesis fails.
That's elegant. It links the mechanics and the thermodynamics directly. Okay, moving to the dynamical Casimir effect, what's prediction 2?
P2 is about coherence-dependent dynamical Casimir yield. Current DCE experiments, they focus on how fast you modulate the effective mirror. MT predicts that if we prepare the SQUID lines with different initial coherence levels, say a highly organized squeezed vacuum state versus a thermal state, the photon pair production rate should depend heavily on that initial coherence state, S-coherent, not just on the modulation amplitude.
So the vacuum's initial state of organization dictates how aggressively it coughs up light when you perturb it.
It does. It says the turbulence, the photon emission, depends on the structured motion you started with.
And finally, we have P3, geometry-driven sign flips. Standard theory already predicts that certain geometries, like specific corrugated surfaces or lens shapes, can lead to a repulsive Casimir force where the plates actually push apart.
This is a huge deal, especially for stiction mitigation in engineering. From an MT standpoint, repulsive force means that the effective mode density between the bodies is actually lower than outside the bodies in the relevant frequency range. You've deleted more standing waves inside than you have outside.
It's a deficit of modes inside the gap, creating a higher pressure from the outside, pushing them apart.
And the MT prediction is that when we realize these repulsive forces, they must show a distinct, measurable spectral signature of missing modes that perfectly matches this motion gradient story. We should be able to measure the vacuum's playlist and prove that certain frequencies are missing or suppressed.
This whole deep dive really boils down to a profound shift in perspective. Hendrik Casimir's plates taught us that the vacuum isn't empty. It's structured motion waiting for instructions. You change the boundaries, you change which rhythms can fit in the gap.
We're not dragging energy out of the void. We are just rearranging which songs the void can sing to keep his books balanced.
Every plate geometry is a playlist for the vacuum.
And the plates move because the universe is constantly retuning its own orchestra to satisfy local boundary conditions. So if forces arise from mode bookkeeping and coherent shifts, if the measurable energy of the vacuum is defined by this ledger, then what other fundamental forces might ultimately be explained by the universe trying to balance its mode ledger? That's the question this physics of organized motion raises,